Hello, my name is Arianne de St-Amour, and here is Permafrost Characterization using ground-penetrating radar for territorial development in Inukjuak, Nunavik. So with the climate warming affecting the high latitudes, there is an increased need of knowledge concerning the cryostratigraphy and the stability of permafrost for land use planning in the inhabited environment. There is a strong demographic growth in Nunavik, which increased the need for housing development and municipal infrastructure. It is therefore essential to proceed to high-resolution permafrost characterization to support urban land use planning and to select foundation designs for building in accordance with local permafrost conditions. Inukjuak is located on the east shore of the Hudson Bay in a continuous permafrost zone, and the community has around 1,600 inhabitants. The research goal is to increase the knowledge concerning the sediment strata in Inukjuak and specifically concerning the nature of the sediments in thaw-sensible deposit zones. The goal is also to compile a map of geomorphological and permafrost features that are key to support decision-making in land use planning and construction. These permafrost features include the depth to bedrock, the distribution of surface geological unit and stratas, and the extent of zones of thaw-sensible and ice-rich permafrost. The research question is combining information already acquired in Inukjuak and the GPR profile interpretations, would it be possible to detect and trace new zones of thaw-stable deposits and new zones of thaw-sensible deposits? There is many geotechnical studies that were carried out at Inukjuak over the years. Many boreholes and surveys that are limited to the active layer up to 1 to 1.5 meter deep. These boreholes were carried out essentially in the early 1980s. There is 4 boreholes that are penetrating the permafrost and are situated in the village that has been carried out by the Center of Northern Studies in 2014 and 2017. And there is also many shallow surveys and stratigraphic sections that were cleared. Superficial deposits were identified during previous studies by the Center of Northern Studies. These deposits are dominated by littoral and nearshore sediments, which are considered thaw-stable. They can be up to 4 meters thick and are characterized by raised beaches and marine terraces scarp. They vastly overlap glaciofluvial subaqueous outwash fan sediments, which are potentially ice-rich and thaw-sensible. The Nastapoca Drift Complex is the main sedimentary unit in Inukjuak. It is generally composed of fine sand alternating with clayey silt bed, and the sedimentation took place during the Hudson Bay deglaciation, forming the Nastapoca Drift Belt. This sedimentary sequence can vary greatly depending on the geographical location, the topography, and the erosion that occurred over the years. And these fine deposits are frequently overlined by sand. With the climate warming, what is to be expected in Inukjuak? Using sample analysis, GPR interpretation, boreholes, and stratigraphic sections, a theoretical borehole has been modelized in order to evaluate the probable evolution of the thickness of the active layer until the year 2100. These models reveal that a rapid increase of the thickness of the active layer is to be expected from the year 2070, according to the scenario RCP 8.5 average. For the GPR surveys, we used GPR model Pulse Eco 100 from Sensor and Software. This it was mounted on a cart equipped with an odometer, and the profile settings we used gain and filter, background subtraction. The survey type is reflection, and the elevation data were added from a DEM, which comes from the LIDAR survey made by Quebec government. And the software used was EcoProject 5 of Sensor and Software. A total of 19.57 kilometers of GPR profile surveyed in the summer of 2015 and 2017 were interpreted. The profiles were interpreted using surface deposit maps, aerial photography, field observation, geotechnical profiling, and boreholes or stratigraphic sections. The field observations were also used to create a collection of known signals such as bedrock, metal pipes and culverts, ice wedges, polygon, and so on. This collection of known signal was used to help interpret profiles for which less trusting information was available. The bedrock, type of permafrost, and type of sediments were identified as often as possible, and the depth to bedrock was estimated using the software EcoProject 5. The velocity was beforehand determined using hyperbolic fitting. The GPR surveys were separated in 3 zones for the interpretation, mainly because there is a higher interference source in the village and in the periphery because of the electric wiring, metallic pipe, frequent cars, etc. And the surveys in the village and in the peripheries are mainly on roads, unlike the surveys on the east shore that are in natural landscape. General legend for the interpretation of the GPR surveys and the stratigraphic sections was made. Here I will show you some few examples of interpretation according to the data available and which strategies were used when few data were available. The first example, in the village, and more specifically in the southwest part of the village, this is a zone where we had very few information. We had no boreholes, no stratigraphic section, few information from the aerial photographs because of the roads and buildings, but there is many GPR surveys and a few bedrock outcrops were identified. Here is the survey number 22 that was carried out in 2017. This is the profile of this survey. It starts on bedrock, and we can see the bedrock going deeper as we go further in the profile. Above the bedrock, we have some sandy sediments that were interpreted as littoral and near-shore sediments. And then we can see some stratification. We have a thick unit of sandy sediments interbedded with silt, and this is interpreted as the unit glaciofluvial subaqueous outwash fans sediments. Second example is in the periphery. We have a profile number 20 that's in the first half of the profile. It is very near a bedrock outcrop, and then it goes in a zone of that was previously identified as tar sensible and ice rich sediments. So this is the first half of the profile. We can see the bedrock, and above the bedrock it's some sandy sediments which is in the stratigraphic unit of littoral and near shore sediments. Then this is the second part of the profile, and we can see that we lose the electromagnetic signal of the rock. And in the first, near the surface, we still have some sandy sediments interpreted as littoral and nearshore sediments. But because of the attenuation of the signal, below the top of permafrost, it was interpreted as glaciofluvial subaqueous outwash fans sediments. There is a borehole that is near the end of this profile, in which the first meter consists of medium to fine sand. So this is consistent with the interpretation that was made for this profile. Here is the third example, which is located on the east shore of the river. This is the GPR survey that goes over a stratigraphic section. This is a few pictures of this stratigraphic section. In the first meter, we have aeolian sand sediments, and then we have approximately 10 meters thick of medium to fine sand interbedded with silt. In the GPR profile, we can see very near the surface in orange some sand dunes, and then below this unit in yellow we have some fluvial terrace sediments. We can see some stratification in this unit, and below this unit we have what was interpreted as glaciofluvial subaqueous outwash fan sediments. So this is the sandy unit interbedded with silt. It's really the stratigraphic section that helped a lot in the interpretation of this profile. A few ice wedges were also detected. These are the little blue triangles. So I've made a typological classification of the electromagnetic signature for the deposits and the permafrost in Inukjuak. There is 7 distinct signatures for the bedrock, the fine and ice-rich sediments, thick and laminated sand, sand dunes and aeolian cover sand, wetlands, metal pipes, and ice wedges. For the bedrock, the electromagnetic signal can penetrate up to 15 meters below the surface. The signature is characterized by multiple hyperbolic reflectors that are made by fractures inside the bedrock, and the planar reflector associated with the top of bedrock is generally undulating. The fine and ice-rich sediments, we can usually see a strong attenuation of the signal. The top of permafrost usually causes a very strong reflector and can create multiples, and the signal can be misinterpreted as interference coming from the surrounding of the survey. For the thick and laminated sand, the signature is quite variable. There is a good penetration of the electromagnetic wave. It can go up to 7 meters deep. We can see some stratification, and there is no multiple hyperbolic reflector, unlike in the bedrock. The sand dunes and aeolian cover sands are only visible at 100 megahertz, and when we can see them, we can usually detect the top and the base of the sand dunes. For the wetlands, they are visible at 50 and at 100 megahertz. It is generally associated with an apparent increased depth of permafrost top, which is due to slower signal velocity. The metallic pipes creates a strong hyperbolic reflector and multiples. And for the ice wedges, we usually can detect a main hyperbolic reflector. Some secondary hyperbolic reflectors also can be detected. We can see an apparent rise of the top of permafrost, and a lack of reflector at the center of the ice wedge because the massive ice is transparent to the electromagnetic signal. So how does this support decision making in land use planning and construction? Well, firstly, it can help create permafrost condition maps. It can also help target thaw-sensible zones across the community and sensible roads and building also in the community. It is important to remember the limits of the GPR. It's the combination of multiple data, field observation, aerial photography, boreholes, stratigraphic section, etc., that allows us to a higher level of confidence in the interpretation. It is still difficult to identify with certainty the thick and laminated sand, and it's very difficult to distinguish the wetland zones from the fine and ice-rich sediment zones. In conclusion, the GPR interpretations has enabled us to detect new zones of thick stratified sand in sector that was previously identified as fine and ice-rich sediments. There is two distinct facies that were identified for glaciofluvial subaqueous outwash fan sediments. The first is thick and laminated sand that are considered thaw stable, and ice-rich clayey silt that are considered thaw unstable. There is a large portion of the village that lies on thaw stable, thick and stratified sand, rocky outcrops, or in soil on bedrock. There is also many rocky outcrops area where building on solid ground is feasible in Inukjuak, but a portion of the village in its eastern half was built on thaw-sensible sediments. And the east shore of the Inukjuak River has many vast and thaw-stable area. So that concludes my presentation. Thank you very much.